Welcome everybody to the online seminar series, Machine Learning Needs Mathematical Optimization. We have the pleasure today of having Nathan Kallus. So he's an associate professor in the School of Operations Research and Information Engineering and Cornell Tech at Cornell University. And he's the research director of the Machine Learning and Inference Research team at Netflix. Nathan's research interests include personalization, optimization under uncertainty, causal inference, sequential decision-making, credible and robust inference, and algorithmic fairness. So really at the core of this online seminar series. He has published in leading journals in the fields such as management science and operations research, and he has co-authored the book Apply Causal Inference Powered by Machine Learning and AI. And his research has received various prizes, including the Inference Data Mining Section Prize. So we are very pleased of having you today here. As usual, Nathan will be happy to take questions during the talk. Please put them in the chat, and I will be happy to pay an eye to the chat. And at the end, you will have a chance of asking the questions yourself. Thank you so much, Nathan, and the floor is yours.
Thank you so much, Dolores. Thanks for the introduction. Thanks for having me. Thanks, everybody, for attending. Yeah, so I thought I'd start with a plug for our new book. We just posted it last week. Yeah, it's all about the combination of machine learning and causal inference, so-called causal ML. It covers causal modeling using such tools as DAGs, SEMs. It's self-contained, so it also covers ML predictions, including high-dimensional regression and flexible nonlinear regression using neural nets and random forests, etc. And then how do you actually do inference in such causal models using this kind of machine learning? So, for example, one of the tools that's covered is double-device machine learning. And the book is accompanied by R and Python notebooks demonstrating all of these tools. So we really hope it will be helpful also for applications and for teaching. But today's talk doesn't have anything to do with causal inference. I mean, in some ways you could say it does, but not explicitly. And today's talk is going to be about learning and optimization. So learning from data and then optimizing to make decisions. And how should we think about those two tasks? Are these separate tasks? Should they be integrated tasks? And we'll see that it depends. This talk is based on two papers, essentially the one paper where there's an emphasis on separation, which is fast rates for contextual linear optimization, with Yichun and Xiaozhe, my former students, and one paper with a focus on integrating these tasks, stochastic optimization force. So the launching off point for our talk is going to be the problem of contextual stochastic optimization, which I studied in an earlier paper from predictive to prescriptive analytics. So in this problem, we're trying to optimize some costs. For example, the travel time from my office to JFK. I'm even trying to get to the airport to fly to give a talk. Luckily, this one was virtual, so I didn't have to travel anymore. And I'm trying to decide which way to go. And the cost, like how much time it will take me to get there, depends on a random variable, on some cost uncertainty, like the traffic or what's happening, the travel time on each of these on this travel network. And because of this uncertainty, I don't actually know the cost, so I'm going to optimize the expected cost, so-called stochastic optimization. Luckily for me, I have access to some contextual information that I get to see before I make my decision, which allows me to reduce the uncertainty in this variable y. So for example, I can observe the weather before I decide how to drive, or maybe I can look on Waze to see, where there might be reports of accidents, etc. And I can use this to reduce the uncertainty on how long it might take me to traverse each edge, and then I can have a better decision z to this optimization problem. So in this, so this is the problem, but the task that we studied in this paper is actually how to solve this based on data. So if you just observe data on the contextual information and the outcomes, you observe n pairs of these x's and y's. How do you use this data to come up with decisions? Right? So one way would be to say, all right, this is just a supervised learning problem. I just need to be able to predict the distribution of y from observations of x. That is, I want to estimate the conditional distribution function. And then I'm just going to plug it in place of the true, right? This expectation is essentially an integral with respect to this conditional distribution function. And I'm just going to plug in a guess. This true problem involves the true conditional distribution. I'm going to plug in a guess. For example, in this particular paper, we looked at linear smoothers. So things like kernels, Loess, random forests, things that can be written in this particular way. So this is a form of a linear smoother that estimates this conditional distribution, and that's how we're going to come up with decisions. Another approach that we studied in this paper is the so-called empirical risk minimization. So rather than directly estimating this conditional distribution, we can say for any policy that's going to map X's observations of the weather, of what's going on ways, to a decision of which path to take, so we call such thing a policy. For any policy, I can look back at my data and backtest it and see how well it did historically, right? So I have a bunch of observations. In observation I would have taken the decision pi of xi. The true uncertainty was in yi, so the cost I would have incurred is this. So I can backtest how well I would have done historically and pick the policy that does the best historically, right? And this is in this particular paper, we look at policies that are given by linear rules, by RKHSs. So in some sense, this one on the left is saying, these are separate problems. First, there is a learning problem, learn a conditional distribution, and then there's an optimization problem. You just plug it in, and then you just optimize. So in this approach, things are really separated. These are two tasks that are treated separately. Where on the right approach, these things are really integrated. It's saying, don't just try to estimate and learn something, but directly learn the decision policy that you want to use. So we're integrating this. We're recognizing that there's some downstream costs, and we're integrating the decision and the learning from this data into one problem. So these are two approaches. And the subject of this talk will be, which one makes sense? Should we separate or should we integrate? What is the right approach to take to this general problem? And because it is a general problem, it's going to depend. So my answer today is going to be, well, it depends on what you're dealing with exactly. So in the first part of the talk, I'm going to focus on the simple problem of contextual linear optimization, where the cost function that's taking in the decision and the uncertain cost is going to be linear. Okay, so it's just going to be the random variable transpose my decision. It's just the inner product of these things. So essentially, the random uncertainty is just going to be a random cost coefficient in a linear optimization problem. Okay, so this is a very special case of this problem that we're going to study in the first part of the talk, and then we'll go to general nonlinear costs. And now that we're focusing on linear costs, so what is an example of linear costs? Well, this example that I mentioned could be written in a linear way if the polytope of decisions is the network flow polytope with a source in my office and a sink in JFK, and then constraints representing the preservation of flow, and Z then is just going to be indicating which path I take, and then I'm just going to sum up the length of traverse, the time taking to traverse each of these edges by taking this inner product. That's all I'm doing. Okay, so that's an example of a linear problem. Another example of a linear problem you could think of is ranking, where I'm trying to put the most relevant item for a user at the top, and then the second most relevant second, and so on and so forth. And there, the polytope of decisions can be thought of as the permutahedron, and maybe the uncertain cost is the relevance or negative relevance, because I'm going to focus on minimization problems, of the item to the user. Okay, so once we have a linear problem, it's a little bit pedantic to write it in this particular way, where I'm saying expected costs given x. Because things are linear, I can take z out of the expectation and make this so much simpler, right? So yes, in concept, right, this is my random cost, which is random cost coefficient times my decision, and then I'm taking expectations of it. Because things are linear, I can just take z outside. Okay? So it's really just some function of x transpose z, where that function of x is going to be the conditional expectation of the vector of cost coefficients given x, right? So the best prediction for the travel time on each edge, given my observation of the weather and ways, etc. Right? It turns out that this function is the only relevant part of the conditional distribution when I'm talking about linear problems. I only really care about the mean. I never care about anything else if all I care about is linear, right? So this is essentially just going to be a linear optimization problem that's indexed by x, because we're going to have a cost coefficient that's a function of x, okay? This true function f star. Now, then we can think about this, well, for every f, I can think about the policy that would choose the optimal decision when I solve the contextual optimization problem when I solve the linear optimization problem with the cost coefficients f of x. Okay? So in particular, the optimal policy is the one that plugs in the true conditional expectation function. Okay? So when we look at it this way, now we can rethink about what does this separate integrate mean here. Separate would mean that we're just going to find a guess for f star. We're going to learn this f star using our favorite machine learning model, whether it's some neural nets, whether it's a random forest, et cetera, et cetera. You can just learn some guess for f star and plug it in. Essentially, just solve this problem where I replace f star by f hat and say that's my best guess for f star. Let me replace it, right? So that would be something like this. So let's take the specific example of non-parametric least squares, which can, for example, include learning on neural nets. So it looks something like this. Given some hypothesis class for the function f star, we're going to call this script f, I'm going to learn a regression function f hat. I'm going to call f hat sub script f because it's going to be the non-parametric least squares on script f. Okay? And it's going to minimize the sum of squared errors historically over my data. Okay? So first I learn just by minimizing errors, completely ignoring the fact that this is going to go into some optimization problem. We're just going to learn a regression function. Right? So for example, this would be, if this were neural nets, I'm just going to backprop the squared error. Right? And notice that I have norms here because y is a vector. It's not a scalar. And then my policy that I'm going to deploy is simply going to be plug f hat into this policy, right? Which says, given an f, plug in, optimize with the costs f of x when you see context x. I'm going to call this ETO for estimate and then optimize, because we're going to estimate f and then we're going to optimize. So that'd be the separate problem. The integrate might look something like this. So before I mentioned just ERM on policy classes, but a really clever idea that was really kind of, it was brought to my attention, I think generally popularized by this paper by Adam and Paul on SBO plus, is there's a really, in this contextual linear optimization problem, there's a very natural policy class to consider as soon as you're going to have some hypothesis class for the function f star. Because if you have a hypothesis class script f for what this conditional expectation is, you may as well consider the policy class given by all the plugin rules. So for every f, I have a policy, pi f, right? So I can think about this induced policy class that's induced by this hypothesis class for script f. And if you think about doing ERM, empirical risk minimization, over this policy, another way to write that is you actually have a different way of learning f. I'm going to call this f check to distinguish it from f hat. So f check is going to not minimize the squared error, but it's going to minimize the cost historically that the policy induced by f would have incurred incurred in the ith example, summed over all the data points. Okay, so that's another way of learning f. Notice these are just two different ways of learning f. In some way, this is aware of the downstream optimization problem. And then my policy will just be to use this f, which is equivalent to doing ERM on this induce policy class. Because I'm calling this an induce policy class, induced by the hypothesis class script f, I'm going to call it IERM, induced empirical risk minimization. Now, importantly, what Adam and Paul do in this paper, and also there's another paper that does a different variant of this thing, is they give relaxations for this optimization problem because it's no longer convex, whereas this least squares problem is convex, right? It's just squares, and we know how to do this, and there's a lot of packages for doing regression supervised learning. Here, it's not clear how to do this, and so what these paper studies actually how to solve this optimization problem in a tractable way. Okay, but I'm going to focus more on the statistics, so I'm not going to focus so much on the tractability, except when I get to empirical examples. Okay, so what is this talk going to be about? So we have these two approaches: integrate, separate. What should we do? So in part one, PAT, there should be an R there. Part one of this talk, what I'll show, well, I'll try to argue, is that surprisingly, the regret of this ETO, this naive optimization unaware approach, the regret that it incurs can converge much, much, much faster, so orders faster. So like think about the exponent on 1 over n, much faster than this end-to-end integrated optimization aware approach. So that's surprising because we'd think, maybe it's better to consider optimization, right? We know what we're actually doing at the end of the day. So there's ways in which it's better. We'll get back to this. There's it's a nuanced landscape, but at least in terms of the regret rates, we can achieve much faster regret rates with estimate than optimize. Okay, and really what's standing behind this theoretically is a very fine analysis that accounts for some instance-specific degeneracy that's going to allow us to see the separation, whereas a more brute force, naive kind of analysis isn't going to see this distinction, even though it actually arises in practice. I'm going to show a simulation very soon, and actually to recover this empirical behavior, we need a very fine analysis to actually see what's happening in practice. And the intuition for why this is happening is, one way to think about this is that somehow we're missing out on some signal in why by just focusing on the policy. And I'll try to make this a bit more concrete. And I just want to emphasize, this kind of sounds like a negative result, like, oh, in some sense, these integrated approaches don't work so well, or can be improved on in certain instances. But really, this is a positive result. Estimate and optimize is so easy to do. There's so many tools out there for just regression. And what we get out of there is really interpretable as predictions. What's our best guess for the the travel time on an edge? It's not just like, oh, it's some black box. I try to find the best policy given these kinds of predictions. But what I get out of f of x is not maybe my best prediction. And more than that, you can support decision making because you can make your decisions based on these predictions. It's literally estimate and optimize is give me your best prediction, and then I'll make a decision based on it. If my constraint set changed, that doesn't matter. My f hat stayed the same, and I don't have to retrain everything. So instead of just saying, some black box is going to make decisions for you, it just says, here's my best prediction. Based on it, you can make your decision. So it's actually positive in terms of practice. In part two, if we'll get there, I want to talk about the general nonlinear cost functions, where in such problems, the solution no longer just depends only on the conditional mean, as it does in linear problems. It may depend on the whole conditional distribution. Now, when we're dealing with these rich data sets where we have, a rich X, a lot of predictive information that we can incorporate, and Y is multidimensional, has the same dimension as your number of decisions, then learning this object, just like forget it. It's not going to happen. It's way, way, way too high dimensional. There's no way you can learn this object reliably without approximating, without saying, oh, this is my best guess in a class, etc. And therefore, I will argue that it makes much more sense to then integrate and look for the best decision in that case, because it's not going to be feasible to learn this reliably. And if you can't learn this reliably, then you don't want to make decisions based on unreliable predictions. So we're going to talk about how to then adapt random forests to solve the integrated learn plus optimize problem. And the key there is going to be tractability, because that problem, even using recursive partitioning for random forests, is going to be computationally intractable, and we're going to need second order optimization sensitivity analysis to come up with a way to make this tractable. Okay, so let's dive in. Let's dive into part one. We're going to talk about just the linear problem, contextual linear optimization. Let me start with a simple example, just to kind of show what this convergence rate thing I've mentioned looks like in practice. So here's a pretty silly optimization problem. I'm going to have context x that are univariate, and they're just uniform on -1, 1, the interval. My response variable, the random cost uncertainty variable, is going to be just x plus some noise. Okay, so in particular, the regression function of y given x is just the line x. Okay, it's this line right here. Okay, I have my polytope of decisions is just interval -1, 1. So literally what I'm doing is I'm trying to optimize y times z. So if y is positive, I want z to be negative because I'm minimizing. And if y is negative, I want z to be positive. Okay, so I'm essentially, this is why it's kind of, I call it an optimization problem in quotes, essentially a classification problem. I'm trying to classify if y is positive or negative. And that's also that sort of intuition of seeing this from the point of view classification will kind of help us down the road when we generalize to optimization problems where I don't have to use quotes around them when I talk about them, but like actual optimization problems. So let's consider a hypothesis class for this regression function. Okay, super simple, just x minus theta, right? So like all I want to know is I know the slope is 1. I just don't know the intercept. Okay, the intercept could be here, it could be here, I don't know. Okay, I want to learn it. So theta equals to 0 is the truth. And for every other theta, right, I'm going to have another guess at this prediction function. If I think about the induced policy class of this hypothesis class, the induced policy class essentially says, I'm trying to classify it's going to be a classification based on the input x, where I'm just going to, based on whether x is below or above a threshold, I'm going to output the decision 1 or -1. Okay, right? Because when x is small, I should pick +1. And if I think about the different thetas I pick, each one will induce a policy, and then I, test it in retrospect, right? So if I pick a theta over here, then it means that in these two examples, I would have picked plus, and in all of these examples, I would have picked -1. Okay, and then I can, compute the cost historically, the average cost, and it looks something like this. And indeed, right, we see that the loss is lowest here in the middle. Indeed, we want to recover a theta that's close to 0. So all pointing in the right direction, except we notice that, right, like between these 2 points, nothing changes in terms of our policy, so nothing changes in our loss surface. Now compare this to the least squares loss that we would use for estimate and optimize. It's going to be strong and convex, and it will change even as we move between these points, and it's going to be much closer to 0. Intuitively, imagine what happens when the noise on these observations, this epsilon, shrinks and shrinks and shrinks and shrinks, right? If this noise shrinks, then the line that goes through these points is going to be unique, and it's going to be the one that goes through 0. So we're going to learn theta equals 0 immediately. Whereas IRM, as the noise shrinks, this curve is not going to change, right? We're still going to have this flat part, still going to be super wide. So it could take us a lot longer to learn what's happening. So that's essentially what's happening here. And if we actually play this out and study it numerically, we actually see this. So if we think about, learning that theta using least squares, then our regret compared to knowing what the true f star is, right? So I'll define regret very soon, but regret is simply going to be the expected costs when we follow our policy versus the expected cost when we follow the optimal policy, then knows f star and doesn't have to learn it at all. Okay, so our regret is going to converge to 0 at a rate of 1 over n. So here I'm showing regret versus n on a log-log scale, and I'm showing the trend line. And the trend line has a slope of -1 on a log-log scale, so that's indicative of a 1 over n-like convergence. Whereas if I look at what IARM would do, right, on this essentially just search over these pi's, the one that backtests the best. As I get more n, I can have better understanding of how each policy would do. So I do end up selecting the right policy. My regret does converge to 0, but the rate at which it converges is slower. On a log-log scale, the trend line has a slope of roughly -2/3. Okay, so this suggests that regret converges as 1 over n to the 2/3 compared to 1 over n, so slower. And if also I would use some approximation of IARM like SPO+, because IARM is generally hard. In this case, the problem is so easy, I just did it by grid search, but generally the optimization problem is hard, right? It might not converge because, of course, it's a relaxation, right? And the cases where we can show that it converges is only in certain cases, not always. So let's try and figure out like how do we actually find theory that backs up these empirical observations that estimate and optimize seems to converge like 1 over n, IRM seems to converge like n to the -2/3. Like can we recover these rates theoretically? So that's going to be the next question. How do we actually study these rates? What kind of regrets rates can we show, and can we compare them? Can we show upper bounds? Can we show lower bounds? Can we show a strict separation? So let's set up the problem. So we're going to look at a decision set that's a polytope. Okay. So you can either write it as the set of z such that az smaller than or equal to b, or you can write it as the convex hull of the corner points of the polytope. So the corner points I'm going to call z angle. Okay. The set of the finite set of corners of z. So examples of such polytopes is the network flow polytope, the femurotahedron that we mentioned before, or simply the simplex. I'm going to assume that the outcome variable y, the cost uncertainty, is bounded. Essentially, I just needed to have nice tails, but we're just trying to make the problem as simple as possible so we can really study it and really gain some intuition. So let's make it bounded without Loftus generality. I mean, whether z is bounded or whether y is bounded is kind of the same, or the how much we bound each one. So let's say y is bounded by 1 and z is bounded by b. Otherwise, we can rescale what's how much big is z and how much big is y. Let us, for the sake of this talk, focus on linear decision rules. Okay, so sorry, not linear decision rules, linear predictions. So things that when we observe a context x, our prediction for y will be some linear transformation w of phi of x. So w is the unknown coefficient matrix, and phi is some known feature representation of x. Okay, so we're going to featureize x. Maybe we're going to use some text embeddings to make it numeric. Maybe we just take x and x squared. Whatever we do, we have some p-dimensional feature vector of transformed features. And then w is going to be the coefficient matrix that's going to transform the p-dimensional features to the d-dimensional outcome variable y. Okay, so this is just to simplify things. I'll focus on linear. And then I'm going to set v of f as the complexity of f to dp. That's the number of parameters that we have to learn. W, that's the number of parameters in this class. And the reason I'm giving it a name v instead of just using dp everywhere is because really, in the paper we generalized to a broader class of hypothesis classes, a new that we give where we give a new combinatorial measure of the complexity, which we call VC linear subgraph dimension, where in this linear case it's going to happen to be dp, but it's more general than that. And this is a particularly useful complexity measure because it can allow us to capture both the complexity of the regression function class and the induced policy class, so we can really compare ETO and IRM, and that's why it's very convenient But for now, let's just put this aside, focus on linear. Okay, so that's the setup. And unfortunately, I think I've deleted the slide where I defined regret. So let me just say in words what regret is. Regret is going to be, as I've said, maybe I can write it. Let's see, let's try this live. Regret of a policy is going to be, can you see as I'm writing it or only when I finish writing? So regret of a policy pi is going to be...
We can see.
Yeah. Okay, perfect. Is going to be the inner product of new instances of y's and x of the cost of taking the optimal policy. So I'm minimizing. So this one is going to be smaller. Yeah, okay. So taking the optimal policy versus taking the policy that I take, okay? Well, it's a bit unwieldy, but that's going to be regret. Loris, this is a nice platform. That was very easy to do.
Thank you.
Right, so this is going to be my regret. So for a given policy, I'm going to see how much did I regret this policy versus the optimal policy, which is going to be the expected cost that it incurs versus the expected cost that the policy that knows f star incurs. Okay, and we want regret low, obviously. So what can we say about regret? So let's talk about upper bounds. So let's talk about upper bounds for IERM. So what we can show is that if indeed pi star is well specified in that it is in this hypothesis class that's induced for the policies, then the regret of IERM is going to shrink, right? Eventually, we're going to find the right policy pi star. It's somewhere in there. And the regret is going to shrink as 1 over root n, or rather, we have an upper bound of a rate of 1 over n, 1 over root n. It also involves the complexity of the function class, right? So in the linear case, p times d. And log number of corner points, okay? And how do we do this? I mean, this is like a standard approach. We're just going to look at the complexity of this empirical process that's essentially controlling how we estimate, how we backtest the value of different policies, and we're going to see how complex could this be as we range over the policies considered. Okay, and we're going to give a uniform law of large numbers for this. And be able to show this result. Okay. We can also give a corresponding upper bound for estimate then optimize. And this is also pretty simple. You take the thing that is our regret, right? This is the expectation of this object is our regret. And then we can just bound it by saying, right, this is going to be bounded by the distance from f to f star in norms. And then, you know, so if our regret is going to be bounded by the expectation of this error, okay, over x, right? Which is simply going to be, you know, by Jensen, we can bound it by the RMSE, and then we just have to plug in rates for the root mean squared error of non-parametric least squares over some hypothesis class. Now, we can't quite plug it in because the results for non-parametric least squares is for we give some new finite sample guarantees for the mean squared error of non-parametric least squares over vector valued function classes, so that we can actually get these rates. But that's essentially a totally, because this is separate, right? This is a separate approach. You just get rates for learning and you plug them in via this inequality and you get rates for the policy making. Okay. And there's a polylog term that we have to take care of in the general VC linear suburb case, but we don't have to suffer that logarithm in the linear case. Oh, yes, and as you notice, both of these are 1 over root n. So, like, what's going on, that doesn't look like the empirical behavior we just observed of one thing converges at 1 over n rate and one converges at 1 over n to the 2/3. Right? For 1 over square root n is slower than both of those rates, and for 2, these are both the same. It suggests that IRM and ETO converge at the same rate, but we just saw empirically that that just was not the case. So what's going on? What's going on is we need some finer analysis. This is just not enough. Okay, this is too coarse of an analysis because essentially it's a very worst case. It's worst case in a sense that may not occur in practice. Okay, so what does that mean? Let me try and explain to you. Oh, and before I go further, let me also show a lower bound that says that in fact, right, it says in words what I just said, this is a minimax rate. In fact, if you think about any algorithm that takes data and gives me a policy, there's going to be some distribution on xy, right? Some instance of the problem satisfying the assumption of the previous slide, right? That pi star is well specified. It's in the induced policy class, such that if the data were really generated from this distribution, then the regret of this algorithm would be at least 1 over root n, okay? Times some constant that depends on the shape of the polytope. Okay, it's essentially like how pointy this polytope is. So this says like we have a 1 over root n upper bound, we have a 1 over root n lower bound. Like that's not what we saw in practice. So what actually is, it seems like it's unimprovable, but what's happening is like, yeah, it's unimprovable unless you make further assumptions. And in reality, we encounter real particular instances, not worst case instances. So what is this thing that we need to account for in this worst case analysis to give rise to what we actually saw in practice? And that's going to be something we're going to call a noise condition, borrowing from the idea of noise conditions from supervised learning.
Nathan, Emmanuel has a question.
Okay.
So, Emmanuel, Nuri is giving you the rights to. Yeah.
Thank you very much. Thank you, Nathan, for your very interesting and clear presentation. I have just maybe very silly question about the upper bound you showed to us for the IERM. So the upper bound involves counting vertices of a polytope in n-dimensional space, right?
With a log.
In d-dimensional space or in n-dimensional space?
D-dimensional space, D-dimensional space.
That's it. So it could be like constant times d,
yes.
The log term, right?
Yes.
So and then the rate of ETO, yes, and this is the argument. No, it's d over n instead of log nd over n.
Thank you for the question. That is not the argument. This is just yes. So in general, this log could look something like linear in D. You might notice it doesn't appear here, but that is not the point. The point is the dependence on n, and how fast our dependence on n is. So there are some
basically
constants.
we fix D. Sorry, we fix D.
Yes, I'm not gonna worry too much about things that are constant in n. Of course, we should worry about them. If there was an exponential in D here or something, we would be like, that bound is completely meaningless and no one should ever care about it. But linear in D, you could say, is reasonable. But in either case, my focus is going to be on the rate in n.
Thank you very much. Thank you.
Yeah, thank you for the question. So in this slide, the point is there is no separation. In terms of rates in n, these bounds are essentially the same rate. Are the same rate, not just essentially, are the same rates. So now the question is, how do we actually go beyond 1 over root n, right? Because the lower bound was also 1 over root n. So the noise condition I'm going to introduce is going to essentially talk about essentially the dual degeneracy of the problem. So think about the linear optimization problem that we have. And suppose we're looking at it over the simplex. So we have a polytope, which is the simplex. We have a cost vector. Okay, so when x is the input, the linear optimization problem we encounter is a linear optimization problem with cost vector f star of x. And it's going to point in some direction. Okay, and actually this is minus f star. Okay, sorry. So this is minus f star where it's pointing. And then the optimal decision is going to be go in the most you can in the minus f star direction, the direction of minus cost coefficients, while staying in the polytope. Okay, so the optimal decision will be this corner point right here. Okay, and then we can think, what is the second best decision? Okay, in this case, it's not quite the second best decision because this whole triangle is feasible. The second best decision among vertices. the second best decision among, the best decision is going to be a vertex. That's just like a property of linear optimization. And then we're going to ask, what is the second best decision among vertices? And that's going to be this vertex over here. And then we're going to ask, what is the difference in costs between these two vertices? That's essentially a measure of how nearly dual degenerate you are, okay? Because you're dual degenerate when they have the same cost. So the distance of the, between these 2 points in terms of cost, so the distance along the direction of f star, we're going to call delta of x. Delta of x is the gap between the best vertex, or the best solution in general, and the second best vertex. That's delta of x. And of course, it depends on x, because for every x, we have a different cost vector. Okay. Now, if we think about it, we have random inputs. X, right? The world is random. One day it's raining, one day it's sunny. And like if we think back to that prediction problem of predicting the length of time it takes me to traverse edges. So I have a distribution of these gaps, capital D of X. And then what I'm worried about is, could these get really, really, really tiny? So it's so hard for me to distinguish the best from the second best in a really, really tricky way. Okay, so what I want to say is, yes, that will happen in eventually, right? Sometimes f star will point perpendicular to this line, to this face, but it should happen only infrequently, okay? So if I think about the distribution of x's, okay, and I think about the distribution, the induced distribution of gaps, big delta of big X, I want to say that the frequency, the fraction of time where it's very, very small, smaller than some delta, should scale roughly like delta to the alpha. So let's think about an example. So think about this picture right here, okay? And I'm going to plot delta of x as x moves. So as x is going to move from left to right, from here to there, f star of x is going to rotate counterclockwise, okay? And as we see that it rotates counterclockwise, right? First we see the gap growing smaller and smaller and smaller as s star is pointing more and more and more perpendicular to the face. When it's perfectly perpendicular to the face, both of these are equally optimal. We have dual degeneracy, but we actually don't mind when we have exact dual degeneracy. That is actually not a problem. What's a problem is near dual degeneracy without actual dual degeneracy. In this case, the gap is actually from this face to this very, very far point. So it's actually, delta is very big. It's actually not a problem in that case. What we're worried about is this case, where we're not exactly perpendicular, but a little bit off, and we think both of these points are optimal, but really one is better than the other, and we're getting tricked. Okay, so that's what we're worried about, being tricked. If they're equally optimal, that's totally fine. Then you can pick either one and you're good. Okay, and then we keep going and keep going, right? And it's going to keep growing and growing. And what is the noise condition saying? The noise condition says, suppose the distribution on X is like some uniform distribution or something with a bounded density, essentially, then the fraction of time that this gap is smaller than delta should be proportional to delta if X has a bounded density, right? Or is, let's say even it's uniform, a uniform distribution. Okay, so that would be satisfying the noise condition with alpha equals to 1. And we argue in the paper, alpha equals to 1 is really like the real practical case. So that's the case that we actually encounter in the empirical example. Alpha should roughly be equal to 1. And that's actually telling us, you know, how often are we in this tricky case? It says, yeah, the tricky case happens, right? This is, delta is going to get arbitrarily close to 0, but we're going to bound how often that's going to happen in terms of this noise condition. So leveraging this noise condition, let me move on so we have time to cover at least the first part. Leveraging this noise condition, these theorems are saying in general you should expect alpha equals to 1 unless your problem is kooky. So generally think of alpha equals to 1 being what's happening in practice. And leveraging this noise condition, we can now obtain what we call fast rates. So let's start with IERM. The fast rates for IERM says that if pi star is well specified, we also need another technical condition that says that it's almost surely the unique solution. Then we can show that the regret is not 1 over root n, but it's actually 1 over n to the power 1 plus alpha over 2 plus alpha. Okay, with some other terms, some polylog in n, some possible linear in d things. And the way we obtain this is via a localization argument. And what we notice is that when alpha is bigger than 0, this is strictly faster than 1 over root n, right? So example, if alpha is equal to 1, this exponent over here is 2 over 3. Aha, that's exactly the n to the minus 2/3 that we saw in practice in a real empirical example. So the theory that we developed really can't pick up the actual performance of what's happening. 1 over root n is actually, a lie. It's a misleading theoretical analysis that doesn't really recover what's happening in practice. In fact, we can give a lower bound that says that you cannot do better than this rate, right? If there's any algorithm, there's going to be some distribution satisfying that pi star is well specified, and now we're going to also impose that it must satisfy the noise condition, right? So this is like the other lower bound, but now we impose a noise condition on this distribution. Then the lower bound is going to be lower, right? It's going to be faster converging in n. But here, notice the lower bound involves the well specification of the policy. And that's really the difference between IARM and ETO. Here, it's all about the policy. Everything that's sort of integrated or end-to-end is focusing on optimizing decision policies. If we move away from that and actually think about learning the prediction, right, doing this separate, just focus on the prediction and then plug it in, we could do much better. And that's the next theorem that says that if the regression function is well specified, then the regressive estimate then optimize is going to be 1 over n to the power 1 plus alpha over 2. Okay, so the way we prove this is via some peeling argument on the regret, and then having some fast rates for non-parametric least squares, and this is going to be even faster than IERM rate, because say when alpha is equal to 1, this is 2 over 2 equals 1. This is exactly the 1 over n rate that we saw in practice before. And 1 over n is, of course, faster than 1 over n to the 2/3. The VC linear subgraph case requires a little bit more delicate handling. We also have some fast, slower rates in a non-parametric case. This is like the VC linear subgraph is essentially kind of like, you can think about a parametric, but you can think about non-parametric classes if you use Holder conditions. Just advertising, there's more stuff in the paper, but let me not delve into it to distract from the point. The point is this simple graph. As alpha increases, the IRM rate stays pretty slow, right? It starts at 1/2 in the worst case. Alpha equals to 0 is essentially a null assumption. We make no noise condition assumption. As alpha grows, the rate gets better and better and better, but never gets better than 1. The estimate then optimized rate, as alpha grows, gets much, much, much better. In particular, the real alpha is alpha equals to 1. That's what we argue is what is actually encountered in practice. It's the kind of instances that are encountered in practice. And then our instance-dependent bounds, these are essentially what the fast rates are. Our instance-dependent bounds give us 1 over 2/3 for IRM and 1 over n for ETO. So we get a much faster rate. So I guess maybe I'll get to just, give the punchline of part 2, but let me try to use my last 9 minutes on some more practical example and some takeaways in terms of practice. Okay, so here I'm just going to take a stochastic shortest path example. So this is like more of a real optimization problem that I don't need to put quotes around. And imagine this is my office at Cornell Tech on Roosevelt Island, and this is JFK, and I could take different routes to the airport. And I'm just going to represent it by a 5x5 graph. My features X are going to be 5-dimensional. This 5x5 graph involves 40 edges, so both Z and Y are going to be 40-dimensional. The true regression function F star, or regression function, conditional expectation function, however you want to call it, is going to be a degree 5 polynomial. We're going to think about different hypothesis classes for script F. Either we're going to think about this magical, impossible, fantasy land of having a well-specified low-dimensional specification where we say, oh, it's linear in degree 5 monomials, so it's perfectly parametrically specified, or this reality of every parametric model is misspecified, so we're going to think about linear in X, which is going to be necessarily misspecified, but it's going to be parametric. Or yeah, you can be non-parametric and maybe you can approximate functions like degree 5 polynomials. So we're going to think about the script F being Gaussian RKHSs, reproducing kernel Hilbert space. And the way we're going to compare all of these methods is in terms of their relative regret. So the regret relative to the optimal policy's cost. And what we see is as follows. So if we look at the correct linear case, this is sort of, just a instantiation of the theory I just talked about. Everything's nicely specified. Things are kind of parametric, so there is that V function complexity that's reasonable. And we see ETO does much better than IERM. For IERM, here I'm using the SPO plus of El Maktoub and Grigas, which I'm optimizing here with Gurubi. Okay, so yes, our relative regret is better. That's just the theory, straight up what it says, exactly like the empirical example I saw before. But that's sort of a guide, but it's not telling the full story. Because what happens when you have a misspecified parametric model, like this wrong linear case? Well, then, if I do estimate then optimize, I'm essentially saying, oh, let's plug in some linear prediction, some true linear prediction, and make your decision based on that. Whereas IRM, it says, yes, linear prediction is not true. It's not the correct prediction. So let me look over all possible linear predictions, the one that gives me the best decision. So then would necessarily do better. And indeed it does better because it's the best rule given by plugging in a linear prediction instead of, the rule given by plugging some wrong linear prediction. So it seems to do better, but I mean, both of these are doing terrible. Both of these, if you have just a wrong model, like this is like, yes, IERM is doing better, but maybe like you shouldn't be using a bad model. You should be using a flexible model if things are misspecified. So that's the story that's told by this RKHS kernel approach. And here we see that, the theory bears out again. If you use regression, flexible regression, you do better when you plug it in. And the estimate then optimize is this red line. It seems to do quite well. It's also converging to 0. It's, of course, worse than perfectly specified parametric model, but it's doing pretty well compared to that. IERM has higher regret. In particular, we can't even solve it with Gurubi. For this kernel case with n above 500, this becomes a completely intractable problem, and we have to use an SGD optimization, which we can't do to full optimality, but to do that instead. We can actually solve it with Gurubi. Yeah, so we do better by using ETO. Let me quickly say in general, if you try to compare ETO than IRM, it's a nuanced landscape. There's different things you might consider. You might consider, what are the regret rates? Well, I just showed that ETO is faster and IRM is slower. That was the main point of this paper. But there's other things to consider. Well, what if things are misspecified? Everything was like mini-max rates here, all I talked about here. All that makes sense only under well specification. What happens if things are misspecified? Well, estimate then optimize. It's got no guarantees. You're just plugging in some wrong prediction. What can you say about that? IRM, you could at least say, yeah, we're not going to converge to pi star, but we can hope to converge to the best policy in this misspecified class that's induced by this misspecified policy prediction class. But if you're misspecified, what you should be doing is just using flexible non-parametric regression that can approximate anything rather than just using some wrong parametric model. So then for estimate then optimize, you can use any machine learning problem. It's completely separable, it's super tractable. Just take your favorite package for doing supervised learning, plug it in. IRM, you have to think about it from the point of view of a hypothesis class. So you have to think about it in terms of a sieve method, and you have to solve this one huge mega problem that is intractable. Interpretability has different depends what you mean by interpretability. For ETO, F is super interpretable. It's really your predictions, and it's reusable, whether you want to do sensitivity analysis of the constraints or think about counterfactuals of what would happen with different constraints. For IRM, the output is not so interpretable. It's just some black box that's making some decisions, but you could say that the model is interpretable if we were to use a very, very simple model. If you were to use a very simple model, maybe you want IRM so you can get the best in class. So maybe you want a very shallow tree, for example. That's a different kind of interpretability. And computation, yeah, as I said, you can use any package for ML. So in 2 minutes, let me just say in words what's happening in the nonlinear case. So once we depart the linear case and we say, no, now C could be a general nonlinear function of Z and Y, now we depend on the whole conditional distribution of Y given X. There's a few examples you can think of what problems like this can look like. Maybe it's a multi-item use vendor problem with some capacity constraints. Maybe it's a mean CVAR portfolio optimization problem. The thing is, now we need to predict the whole conditional distribution, which is a very high dimensional and generally challenging problem. So there are non-parametric methods like kernels and stuff like that. That is sort of what was studied in our earlier paper from predictive to prescriptive optimization and analytics. I forget anymore even. I called that paper, and those are those linear smoothers. So that can be very impractical. It can suffer from the curse of dimension. This is not comparable to sort of large-scale modern ML. There's a practical recommendation with not a lot of theory in the paper of, oh, what if we use a random forest as an adaptive kernel to plug in for a linear smoother, okay? And that seems to work in practice in some cases. It doesn't work everywhere, as we'll show in this paper, but it's sort of doing the wrong thing. It says, oh, use a random forest problem to learn the conditional expectation function, but then use the weights in something that depends on the whole distribution, and in particular for an optimization problem. Like you couldn't even think about random forest to learn conditional distributions, but we don't even want conditional distribution, right? That's the thing that we said, it's too hard to learn, let's avoid that. So I'll just end by saying what we do in this paper is figure out how to train the forest trees to recursively partition the trees in order to optimize the decision quality, not the mean prediction quality. And the key to doing that is making things more tractable, because even with recursive partitioning, this problem is computationally tractable, and we need some clever approximation. I have a slide here saying what are the contributions of that. Here we go. Here's our solution. So we developed this optimization, this method based on second-order constrained optimization perturbation. We call this the stock opt forest algorithm. We show it's computationally tractable in a variety of examples. We show that this approximation is a consistent approximation. We show that the algorithm is asymptotically optimal as the forest gets big, and we demonstrate things empirically. In particular, we have some experiment on some Uber data for this risk-sensitive shortest path problem. I'll just end on my recap slide. I'll just put this up there. I'm already over time, so I won't talk through it. I'll just kind of remind us of the theme of the talk. With the problem of contextual stochastic optimizations, there are two general approaches to solve this problem when we're faced with, how do we actually learn to make decisions in a CSO problem. Either we can separate this, we solve the prediction problem separately, where we learn how to predict Y, its mean or its distribution, whatever it is we need, given X. In the learning part, we completely ignore the fact that there's an optimization involved, and then we just plug it into the optimization. Or we could integrate things. We could learn a predictive model that would optimize the risk of the policy it induces downstream. And the question is, which one is better? And the answer is, it depends. Okay, thank you so much. I'm happy to stick around for any questions, but I understand people might have to go. I'm already 2 minutes over.
Thank you for the great presentation. And to the audience, do you have any questions? And remember, if you raise your hand, then we will give you the rights for the camera and the video and the microphone. Apologies. Wonderful that you were able to compact so much material in 1 hour.
Well, I think it's of course about what you. It's not about what you cover. It's about what you uncover. So I hope I uncovered something and not just covered a lot of material.
I think at this point there are no questions, but you gave us a lot of food for thought. It was an amazing presentation. So I think we are going to leave it here. And as you know, this is being recorded. We will place it in the YouTube channel that we have. And yeah, you will have even more viewers over there, I'm pretty sure. Yeah, so thank you so much for making the time today.
Thanks for having me.
Yes, thank you. And to the audience, remember that next week we are back with a young session with 3 young speakers, and we would love to have you back on Monday. Thank you all.
Have a good day, everyone. Bye.
Have a good day.